Hello everyone, I'm Shimon Yu from Georgia Tech. Today is my great pleasure to be virtually invited to attend this conference. I'd like to share some of our research progress in the field of ferroelectric transistors for synaptic devices. We're going to talk about the challenges and prospects offered by this emerging technology. Here are the motivations to develop the specialized hardware accelerators for artificial intelligence or machine learning workloads. As we know, GPU is still dominating the training in the cloud, and we see that FPGA is becoming a popular platform for the inference, especially for fast prototyping. And also, there's a new trend to develop the digital ASIC platforms, for example, the Google's TPU, to perform the accelerations at the cloud as well as the edge. So if you look at the different computing platforms, the energy efficiency varies or not. So here the energy efficiency is using the metric tera operations per second per watt or TOPS per watt. And the conventional computing platforms like GPU is about 0.1 TOPS per watt, but it can support the floating point computation. And the digital ASIC platforms like TPU or the equivalents can achieve like 1 to 10 TOPS per watt. But it can support the fixed point computation. If we want to further increase the energy efficiency to like 10 to 100 TOPS per watt, we believe that computing memory technology is a promising paradigm. So here we are going to use the analog computation within the memory array. The memory can be CMOS, like SRAM, or the emerging non-volatile memories. And then we have to embrace the low precision computation. And then the question is, can we achieve the same accuracy as the digital platforms? We are going to discuss those issues in the presentations today. The key idea of computing memory is to use the crossbar array to accelerate the weighted sum and weight update process in the neural network model. So here we show an example of the one-layer network to be mapped to the crossbar array. So here the weight of the network is mapped to the conductance of the memory devices. And then the input vector x is mapped as voltage to enable multiple rows. And then the voltage multiplied by the conductance of the device will result in the current to be summed up along the columns. And then the output will represent the weighted sum. We may need to use the analog to digital converter, the ADC, in the peripheral circuits to digitize the analog output. But we can do this process in parallel, so we can speed up the vector matrix multiplication. This is for the inference stage of the neural network model. And if we want to train the neural network, that means we have to update the device's conductance frequently by using the pulsing scheme, which is determined by the learning rule. And we can translate the delta W to be the number of pulses to be applied to the device. There are several kinds of emerging non-volatile memory that can be engineered towards the resistive synaptic devices to be used in the crossbar array. And here we show the examples of the filamentary R1, where we form the conductive filament in the oxide material. And generally, in this kind of filamentary R1, the set process is abrupt. That means it's hard to achieve multi-level states, which is typically required in the synaptic applications. The second candidate is a non-filamentary R1. In this case, we rely on the diffusion of the defects between two kinds of oxide layer. Typically, this kind of non-filamentary switching is slow, and the retention may be poor. The third candidate is a phase-changing memory, where we can switch the crystalline phase and the amorphous phase by the heat pulse. And in this case, the reset will be abrupt because we have to melt this material and then go through the quench process. And the last candidate is the ferroelectric field effect transistor, FeFET. So in this case, we replace the gate oxide with a ferroelectric layer, and then we can partially flip the domains in the ferroelectric layer, so we can fine-tune the threshold voltage of the transistor, where the conductance of the channel can represent the weight. So in this case, we have better control of the weight tuning by the gate pulse, and then the read and write paths are decoupled, so then the reliability may be improved. And we will see that in today's talk, the FeFET is a suitable candidate for the resistive device. Here's a wish list for the ideal synaptic device. First, we want the device to be as small as possible, less than 10 nanometer in dimension. Second, we want the device programming voltage to be compatible with the logic power supply, about 1 volt. Third, we wish the device have multi-level states, let's say larger than 64 states, or equivalently 6 bits. This is required for the training. And also, we prefer the device to have linear and symmetric updates to achieve good training accuracy. And this requirement can be relaxed to be 2 bits, 4 levels for inference. And then the device dynamic range or on-off ratio should be larger, let's say 100. And then the device on-state resistance preferred to be in the range of 100 kilo ohm to 1 mega ohm to minimize the read dynamic energy and maintain reasonable readout speed. The device energy consumption for the programming should be less than 10 femtojoule per pulse. And then device retention should be good, larger than years for inference. And then the device endurance should be larger than 10 to the power 6 updates for the training. Of course, all of those numbers here are application dependent. That means we have to consider the problem size, the data set, and so on. We want to claim that the ferroelectric transistor FeFET can meet most of the requirements in the previous slide, probably except the programming voltage. Here we want to show a pioneering work by my collaborator, Professor Suman Datta's group at the University of Notre Dame. So here they published the first analog Synapse based on the FeFET in the IEDM 2017. So here the transistor is a non-channel transistor based on the HZO gate stack. The hafnium zirconium oxide is a well-known ferroelectric material, and which is CMOS compatible. So in this case, we can use the pulse to the gate to partially polarize the HZO thin film. Then we can result in different threshold voltage in the transistor's transfer curve. Here you can see that at the fixed gate read voltage, then we can have different conductance read out from the channel. Then we can use this conductance to represent the analog weight in the synaptic device. Using this device, we demonstrate the symmetric and fast weight update. As you can see here, we apply the pulsing scheme with varying pulse amplitude, but with 75 nanosecond pulse. So we can potentiate the device's conductance following this trajectory, and then we can depress the conductance following this trajectory. So it's quite symmetric respect to the potentiation and depression. And in total, we can achieve like 32 states, that means 5 bits in this FeFET device. And then this right-hand side shows the IDVG curve of the corresponding multi-level states, and you see the gradually changed threshold voltage. So far, we talked about the motivation and background for using the FeFET as the synaptic device. And in the next couple of slides, I want to address one challenge we found in the FeFET device for synaptic application. That is how to accurately tune the intermediate states. The challenge aligns with this history effects in the minor loop switch. So what is the history effect in the minor loop switching? Let's look at one example from the ferroelectric capacitor, FeCap. So if we use a precise model to do the simulation of the minor loops, we can have the following results. Let's assume the waveform applied to the capacitor following those two kinds of trajectory. So the small loop starts from S0 state, and then it will go up and then come down to the S2 state in this polarization versus voltage PE curve. And then the large loop will start from the same S0 state, but then it will be polarized to a larger S3 state. And then the S3 state, if we apply negative voltage, then it will come down to the S2 state. Now here we have two possible transitions from the S2 state back to the S1 state. But if we follow the small loop, the red curve, then the voltage to change from the S2 state to S1 state is the voltage Vc. And then if we follow the large loop, then the voltage to switch from the S2 to S1 will be this voltage Vd. And then we can say that the voltage Vc and Vd does not equal. So this depends on the history of the device, even though we have the same transition from the S2 to S1 state. And then we experimentally validate this kind of history effect by using the FeCap devices. And here we showed several samples with different kinds of waveform trajectory. And here you can see that the voltage indeed to switch from the S2 to S1 state will vary, depends on the prior path it has gone through. So here, for example, the smaller loop use negative 1.19 volts to switch, but the larger loop need to use negative 1.5 volts to switch. Similarly, you can see the voltage is different in other examples. We also validated the history effect in different measurement setup. For example, here if we change the sweeping polarity to the positive side, we also see that the different loops may result in different switching voltage even from the same transition from those two intermediate states. And we have seen this kind of trend in different samples. And also if we change the sweeping frequency of the triangular waveform here, if we increase the frequency, then we can see this kind of PE curve. But again, the voltage to switch between those two states vary, depends on the prior path the device has gone through. So we would argue that the history effect is universal in the FeCap. Not only FeCap, but also FeFET shows the history effect. So here we experimentally validate the minor loop switching on Globalfoundries 28nm high-k metal gate FeFET samples. So here we first consider a large loop, and we first program the device to the G3 state, and then we reset the device to the G2 state, and then we reset to the G1 state. So here we use negative 2.8 volts on the gate to reset from S2 to S1 state. But if we consider a small loop where we directly change from the S2 to S1 state, even though the conductance change is similar, but the voltage we require to change will be different. So here we only need negative 2.5 volts to change from the S2 to S1 state compared to the larger loop where we have gone through the S3 state. And we can consider a different minor loop where we start from the same S2 state, but if we keep using the same voltage, let's say negative 2.8 volts, then we are going to result in a much more reset state. This one, the conductance will be like 11.2 nanosiemens, but previously it's only 0.19 microsiemens. So here we can validate similar minor loop in different samples. I will skip the details of the other samples, but again, this kind of history effect is universal in FeFET as well. So what causes the history effect? Here we use the phase field modeling to simulate the multi-domain switching considering the variations in the coercive field of each individual domain. And we use this time-dependent Landau-Ginzburg framework to simulate the evolution of the domain polarization switching as follows. First, we consider the larger loop where the device has gone through the S3 states and then S2, S1. The minor loop will directly switch from the S2 to S1. If you compare the two loops on the same state, S2, they have similar average polarization value, about 0.6, but the internal domain configuration is different. Later, when we switch to the S1 state, which also have similarly average value, about 0.6, but the internal configuration again is different, and the voltage or the electric field to switch from the S2 to S1 is different in this larger loop versus this minor loop. This agrees with the experimental data we have shown earlier. I'd like to give you a more intuitive understanding what's going on here. We can use this cartoon figure to show the different coercive field of the multi-domain in the device, where we call the domains with larger coercive field as hot domain, and the domains with smaller electric field as easy domain. So in the larger loop, the device has gone through the S3 stage, where most of the hot domains have been flipped down. Later, if we want to change from the S2 to S1 state, then we have to flip those harder domains. That means we have to use larger electric field. In the minor loop, even though at the S2 state, the number of domains flipping up and down will be the same, but those domains mostly are the easy domains. So later, when you switch from the S2 to S1, you just need to flip those easy domains. Therefore, the electric field to flip the domains will be smaller. So we can understand the history effect using this chart. So the history effect may negatively impact the neural network training accuracy. This is because if we switch between the intermediate states, it's really hard to track the device's history. Therefore, it's almost impossible to design the voltage to accurately tune the device to the target conductance state. Therefore, we result in the error in the weight update. To quantify this kind of effects, we built a compact model incorporated into the neural network training flow, as shown here. And then we use MNIST dataset as a recognition task to test the training accuracy. And we see that only 91% accuracy can be achieved if we consider the history effects of the weight updates. To mitigate this problem, we propose a new protocol that is to always erase the device to the ground state before the next programming. Therefore, the device will always operate along the saturation loop. If you do this fully erase before program, then we can see that the training accuracy can be recovered to the 97%, which is close to the software baseline. Of course, the overhead of this new programming protocol is additional erase pulse, which means longer latency and larger energy. The other challenge of using FeFET for the neural network training is how to enable individual cells programming and erase in the FeFET array. This is because normally the array shares the body. Therefore, if we use the body erase, then the whole array will be erased together. To mitigate this challenge, we propose a drain erase scheme. So here is a proposed programming and erase scheme to enable the individual cells with updates in the FeFET array. And here we can see that we use the gate to program the device, where we apply 3 volts to the word line, and then we ground the source line and bit line. So the device will receive a positive potential drop across the gate stack. So this will program the device. And in the erase, we are going to ground the gate by applying 0 to the word line, and then we raise the potential of the bit line to be 3 volts and the source line to be 1.5 volts. So effectively, from the drain to the gate, we will have a negative 3 volts. Then we can effectively erase the device. We need to examine the possibility of the drain erase in the next slide. We characterize the drain erase scheme on Globalfoundries 28nm high-k metal gate FeFET and 22nm FDSOI FeFET. So here this is a waveform we applied. We are going to bias the source to be 1.5 volts or 0, and then we will apply the drain pulse. So here, as we increase the drain pulse amplitude from 1 volt to 3 volts, we can see that the drain current effectively decrease. That means the erase is successful when we increase the voltage to 3 volts. And here is a bias condition again. The gate is grounded and the drain voltage raised up to 3 volts. The erase is successful. And then we can vary the pulse amplitude and pulse width to draw this kind of 2D phase map to show the erase is successful from the initial 1.1 micron M to the eventual 0.14 nanoM. So we achieve 4 orders of magnitude on-off ratio by varying the pulse width and pulse amplitude. But also we can see other testing conditions. For example, if the source is grounded, then the on-off ratio is not very large. That means we have to increase the source to be half bias, 1.5 volts. And also we can examine different device W over L. The drain erase scheme is also effective. And then the last one is the high-k metal gate buck devices. Unfortunately, the drain erase is not very successful in this buck device compared to the FDSOI device. The reason is that the FDSOI has a confined channel, so the drain voltage can effectively raise the channel potential. Therefore, we can have negative voltage drop across the gate stack to enable the drain erase. The drain erase is effective to the selected cell, but also we need to consider the inhibition to the unselected cell in the array. So here, for example, if we have the drain voltage applied to the unselected cell, then we need to apply gate voltage to inhibit the cell from being erased. And here we experimentally validated the inhibition condition. For example, if we bias the gate to be half of the drain voltage, then we can see that the transistor still maintain large drain current. That means the device is not erased. And we repeated this kind of inhibition condition for many erase cycles up to 10 to the power 6. Still, the current maintains high. That means the inhibition is successful. Finally, we want to show the prospects of the FeFET-based computing memory accelerators by system-level benchmark. We are going to use the DNN+Neuro Sim Framework to do the benchmark. So this is an integrated framework of the Neuro Sim with the Pytorch and Tensorflow. The Neuro Sim core is a circuit model that is built upon a hierarchy of the chip, tile, processing elements, subarray, with all the necessary peripheral circuits, including the ADC. And we calibrate the technology parameters with a PTM model from 130 nanometer down to 7 nanometer. And the Neuro Sim can report the energy efficiency, throughput, area, and memory utilization. And then we use a Python wrapper to interface the Neuro Sim with the Pytorch and TensorFlow, which are popular machine learning packages, where we can define arbitrary and deep neural network model and report the inference and training accuracy under the hardware constraint. For example, we consider the device retention model and also the ADC quantization effect for the inference accuracy. We can also consider the device nonlinearity, asymmetry, and the variation effects on the training accuracy. So the source code of the DNN+Neuro Sim is publicly available from those GitHub links. And there are two versions. The latest one is V1.2 for inference and V2.1 for training. And this is the hierarchy we modeled in the Neuro Sim framework. Consider the FeFET-based subarray, and then we have the peripheral circuits like ADC, shift and add, and the multiple of this subarray will form a processing element, PE, with the adder tree and input and output buffers, and the multiple of the PEs will form one tile with the routing and also the input and output buffers, and then multiple tiles will form a chip, and at the chip level we consider the global buffer and neural activation function and the pooling function. So with this simulator, then we benchmark the inference accuracy if we use the FeFET-based design. Then here, one important parameter is to determine the ADC precision. And as you can see that this is for the CIFAR10 data set. If we assume the array size is 128 by 128, then consider the multi-level per cell, then we need 5 bits ADC to maintain the baseline accuracy. And then this is the radar plot showing the trade-off between different metrics like the accuracy, area, energy efficiency, throughput, and memory utilization. So if we assume the FeFET can achieve 4 bits per cell, then we want to use 5-bit ADC. Here is a system-level benchmark result for the VGG8 neural network model on CIFAR10 dataset. First, we benchmark at 32 nanometer node because today most of the non-volatile memory are integrated at 28 nanometer node or 14 nanometer node. And here we consider different candidates, including the SRAM and RRAM and phase-changing memory and ferroelectric transistor. And we extract the parameters from the literature. And first, we look at the metric like the area, energy efficiency, and throughput. You can see that the non-volatile memories with large on-state resistance, for example, here hundreds of kilo ohm, then the energy efficiency will be much better than those with small on-state resistance. And also the throughput will be higher compared to the SRAM as a same technology node. And we need to consider the state of the art because SRAM has been scaled down to 7 nanometer or beyond. So if we project the FeFET can be also scaled down to 7 nanometer, then this is a benchmark result. If we compare the FeFET at 32 nanometer versus a 7 nanometer SRAM, of course, 7 nanometer SRAM still achieve better energy efficiency and throughput, of course, much smaller area. But if we can somehow scale the FeFET to the 7 nanometer as well, then we can achieve even better energy efficiency and throughput compared with the 7 nanometer SRAM counterparts. So here the conclusion is that if we stay with 32 nanometer node, the FeFET outperforms other non-volatile memory candidates, including SRAM. But if we want to compete with the 7 nanometer SRAM, then we need to scale the FeFET down to more advanced technology node. Here is a summary of my presentation. We see that FeFET is a promising candidate for the Synaptic device to enable the computing memory, and also the deep neural network in-situ training require the weight update to be symmetric and linear. To accurately tune the FeFET into multi-level states, we need to overcome the history effect, where we propose an erase before the programming scheme is needed. And also, we need to enable the individual cells programming and erase in FeFET array without disturbing other cells during the in-situ training, where we propose the gate program and drain erase as an effective method. Finally, we present the DNN+Neuro Sim benchmark results to show the great potential of FeFET-based accelerator. If we can scale that down to 7 nanometer, it will be even more competitive over 7 nanometer SRAM. With this, I'd like to thank my collaborators in this research, including Professor Suman Datta from University of Notre Dame and Professor Asif Khan from Georgia Tech. Of course, I'd like to thank the students and postdoc involved in this research. And this research is in part supported by the SRC JUMP program, in particular, the Ascent Center. If you have any questions regarding this presentation, feel free to send me an email by this address. Thank you so much for your attention.